In this video, we're going to talk about surface integrals. This is an extension of surface area, which we've talked about previously. Now, the generic notation I'll use for just surface area is the double integral over a surface d sigma. D sigma here is thought of as a little element of surface area. So I'm just saying add up all the little elements of surface area. This is a great definition, and it's much like how previously we would often talk about the arc length parameter ds, which was great for definitions, but wasn't how we typically computed things. So in our previous video, we've talked about how to compute this in a few different cases. First, there was parametric. If your surface was described parametrically, some position function r in terms of u and v, then your surface area could be computed by taking the double integral of your integrand being the length of the cross product ru cross rv du dv. And so the combination of the cross product and the du dv is our little element of surface area when it's described parametrically. Alternatively, it might be described implicitly with some big function capital F of x, y, z equal to c, a level surface. And when that was the case, we've previously seen the surface area could be written as the double integral of the length of the gradient of f divided by the absolute value of the gradient of f dotted with the vector p, which was often k hat, but could be I hat or j hat as well. And then finally, we saw that when it was described explicitly, z as a function of x, y, it could be described as the double integral of square root of fx squared plus fy squared plus 1. So the point is, 3 different ways to describe a surface, 3 different methods to compute out the surface area of that surface. Okay, so that's what we did in the past. Now let's go to the concept of a surface integral. And the idea here is I have some new function, I'll call it capital G of x, y, and z. And this is the function that is defined on that surface. So at any point on the surface, there is a height, if you will, the value of this function, g of x, y, and z. It's a little harder to visualize this as a height now because your surface might live in 3 dimensions, so the graph of this would be a 4-dimensional object. But regardless, I want you to think, at any point along the surface, there's some value of the function. Then a surface integral is adding up the values of that function along each little element of surface area. That is, it's the double integral along the surface of the function g d sigma. This is exactly analogous to the concept of a line integral, which would be the integral of some function ds. And then I can return to my 3 different ways of describing it, and 2 things have changed. First, instead of surface area, I'm writing SI for surface integral everywhere. And then I've gone and I've put a g into the integrand every spot. So this is double integral of g times whatever the d sigma is for the 3 different presentations. The g's look a little bit different, and it's just to reflect the type of computation I'm doing. So when it's done parametrically, the 3 different components are written in terms of the parameters f of u and v, g of u and v, and h of u and v. When it's implicit, you can just write it in terms of g of x, y, and z, as we had before, that's fine. And when it's explicit, well, since the z is f of x, y, I'll write g as x, y, and f of x, y in for the 3rd component. Regardless, it's just putting a g into each of these different places. Okay, so let's see a couple applications. First application is the mass of some surface, some thin shell. For example, I've drawn this cone surface, and I want you to imagine that at some spots, this material that's used to make that shell is thicker than at other spots. For example, if you're making a pottery bowl that's spinning on a wheel, some points you squeeze in and the wall is thinner, some spots it's a little bit thicker. So you can have a sort of a variable density, a variable thickness as you go along. So then if you had that, so I'll let delta of x, y, and z be the mass density of my thin shell, then the total mass would be adding up the density times the area. So in other words, it would be a surface integral. That is the double integral over the surface of integrating this density function, the sigma, that is for a little element of surface area. A second example I'm going to use is actually involving a type of averaging. So I want to imagine that there's a temperature at any point on the surface of the Earth. Imagine that's a sphere of radius a. I'm going to assign a particular temperature. It's kind of like saying you have a height above the Earth, except instead of height, it's a temperature above every point on the Earth. And then I just made up some sort of quasi-realistic temperature function. It's really not that good. But I'm basically just saying that if phi was 0 or pi, so the North and South Pole, the temperature would be minus 20. If phi was pi over 2, aka along the equator, then the temperature would be minus 20 plus 50, which is 30. Okay, sort of works, I guess. Anyways, if I want to figure out the average temperature, well, what's the formula for any average? It's you add everything up and then you divide out by the number, right? If I wanted to compute the average grade in the course, I'd add up all the scores, divide out by the number of students. So the average temperature here is I'm going to add up all of the temperatures on all of the little elements of surface area and then divide out by the total surface area. So the 1 over 4 pi a squared is me dividing out by the total surface area. And then I've got this surface integral where I'm adding up all the temperatures, the integral of the temperature function d sigma. Okay, so now I want to compute that out, so I guess I should put in the actual temperature function I have. And then this is described parametrically. I'm imagining my surface here in the phi theta parameters. And so I know what they are in spherical coordinates. The phi goes between 0 and pi, and the theta between 0 and 2 pi. And then the most important part here that's being added is this a squared sine phi. That corresponds to r phi cross r theta. And we computed that before. As in a previous video, we computed the surface area of a sphere. We had parametrically described it in exactly the same way. And we'd come up with this formula that we need to do when talking about surface area parametrically. It's the r phi cross r theta. That exact thing comes up in surface integrals as well. And so since I've already computed it, I'll just assert it for you. It was a squared sine phi. Now this is just a double integral. I suppose I can go and try to clean it up a little bit here by just expanding everything out. And then for the integrand, well, okay, minus 20 sine phi, nothing happened there. But I do have a sine squared. And so I get to use the trig identity of 1/2 1 minus cosine of 2 phi at that spot. Regardless, after that, trig identity is really just sort of born in computational. So the final result I'll give is this. Notice there's an a squared on the top and the bottom. Cancel the a squareds. It's a number about 18 degrees Celsius. So in my made up temperature function for the surface of the Earth, the average temperature on the Earth is 18 degrees Celsius. It's worth perhaps noting that the minimum temperature in my model was minus 20 and the maximum temperature in my model was plus 30. And the average temperature of 18 is like way, way, way closer to the 30 than it is to the minus 20. So why might that be? But if you think about the Earth, yes, it's minus 20 at the poles, but the surface area around the poles is pretty small. Whereas the surface area around the equator is actually really big. It's proportionally larger surface area in the values of phi that are nearby pi over 2 than are nearby the 0 or the pi. And so that's why the average sort of gets weighted a little bit. It gets weighted more towards the top end than to the bottom end. Regardless, this is just an example using the parametric formula to come up with a surface integral. We can do the exact same thing for the implicit or the explicit as well.